So the problem mainly asking is car fleet. So they all have a final position for them to actually travel to, which is target equals to 10, which is this spot over here. So the thing about the tricky thing about this is that you say a car is like traveling slow than the previous, it will collide with the front vehicle and then move with the speed of like the vehicle 1. So this vehicle 1, vehicle 2 will start to actually go to the speed of vehicle 1 because vehicle 1 is slow and vehicle 2 is fast. Vehicle 2 has to actually coincide and actually obey with the speed with the car vehicle 1 because vehicle 1 is in front of him. And we sort of like rinse and repeat for the rest of the vehicle. And for this case, there's like a third vehicle. Third vehicle runs very fast. It runs faster than even 2 and even to 1, obviously. But the thing is this, that your vehicle 2 is already coincide with like the vehicle 1, so you can kind of like ignore vehicle 2 already because it gonna go travel same speed as 1. So now let's compare two vehicles, because comparing two vehicles is so much more simpler than comparing three vehicles, right? So now we compare the two vehicles, vehicle 1 and vehicle 3. So vehicle 3 also runs very fast. It runs at 2.3. So the moment it reaches vehicle 1, it will coincide and actually run at the speed with the vehicle 1. And that's the whole gist of this problem, which is that we actually want to actually calculate, I think is to do with will there be a car fleet, and then how bad is the car fleet? So how many of these vehicle is being car fleeted? So obviously 2 of it being car fleeted, because at the end of the day we all traveling at the speed of vehicle 1. So you can argue on the second point, which is that say that what if there's like no car fleet? So there can be a case whereby basically the vehicle 3 is traveling maybe very slow speed, so it doesn't matches the vehicle 1 per se. So in your stack you will actually find out that you still have like 2 values that's valid. But when you talk about this case problem statement, you only find out that there's only vehicle 1 left, with the vehicle 2 being popped, vehicle 3 being popped, and then the stack is just one value by itself. So if you compare 1 and 2, the difference is this, that 2 will have 2 values in, because vehicle 3 still exists over here, and then we have also the vehicle 1. But for case 1, it's just left with like just one vehicle, because V2 and V3 is being popped because they were being car fleeted. As for this, only V2 is being car fleeted. So the main problem is also just basically asking how many vehicles being car fleeted. So for this problem case statement is that 2 vehicles being car fleeted. So now, since we discussed this, I think it's also good to actually discuss first and foremost, why do we use a stack? And then what is actually the condition that is being set for this case itself? So obviously, when I actually see throughout this whole entire issue, I just see that the first intuition that I actually think about is actually hash map, because it sort of check values between the time reached for vehicle 1 and vehicle 3. So my intuition is telling me a hash map is kind of like necessary. That's my hypothesis. And the second item that I think it kind of links I mean, they already actually mentioned there's a stack, but how does this stack actually play into the role play of this whole problem statement? Um, I think one thing about it is definitely to do with convenience, but I don't think this is like a very convincing idea to actually convey. More functional thought on I think is to do with the I think that the order do actually matter for this case scenario. So I gonna actually try to actually find why is that. So my very first clue is actually we do a sorting for based on like the position and the speed. I mean mainly based on the position actually. And the second key idea that capture my attention was the 1 and the 2, which having said that the vehicle 1 will always be placed at the most bottom places, and the most bottom place is actually to do with this A over here as well with regards to like the position. And another item that I think we can actually talk about is over here, where we see vehicle 1 is right at the very start, and that everything will always be sort of limited bottleneck by this vehicle 1. So these two vehicles actually need to take into consideration of like the front vehicle. Not per se is to do with like the most front vehicle, but any vehicle that is like in front of you, you sort of get affected by it. So I mean, if we were to actually talk about like the basic properties of like a stack, is that each element is actually get affected by the front element. So you for the this element, maybe say for element 1, you need to wait for the element 2 to be popped so that you can pop the vehicle 1, right? So technically your second element is affecting your first element, and for the third element is that the second element need to wait for the third and the fourth element to be popped so that it can actually get popped. And if you were to actually see that vehicle 1 is actually element 1 is actually waiting for element 2 to be popped, and element 2 there's like a chain cycle that is like always waiting for the top element to be popped. So technically if 1 is waiting for 2, 1 is actually waiting for the entire series of the 2, 3, 4 to be popped so that 1 can be popped. And similarly for 2, in order to wait for the 3 to be popped, it actually need to wait for the series of like the top series of like elements to be popped so that 2 can be popped. So in fact it actually need to wait for 3 and 4 to be popped. So what I'm actually trying to actually say is this, that 1 is actually waiting for 2, but 2 can be waiting for 3 and 4. So in fact 1 is also waiting for 2, 3, 4 to be popped. So I think we can see sort of like the similarity for this basic principle of Z, and for this case Y, the similarity between these two. In Y, we actually did discuss about having the vehicle 1, the 2 to be constrained by the in front vehicle 1, and for 3 it's been limited by both the 1 and the 2. And similarly for Z's case is that 1 is like being limited by 4, and 1 is also being limited by the 2, 3, 4 to be popped, then it can actually get popped. So in this case I just feel that there's some sort of like similarity between the Z and the Y. One thing that is concern to me is the hash map. How do we actually use this hash map to play into our Y? Obviously in why they do actually talk about if we were to zoom in, they actually talk a lot about using the final destination, which is the target 10, that on how much time is required for vehicle 1 to actually travel to the final and vehicle 3 to travel to final. So obviously the time required for this is 2.3. Here time equals to 3. So maybe one of the conditional statement is just basically simply don't need the hash map, but rather just set a conditional statement of saying that if the element is more than your time 1 is more than time 3, then we pop. If not, we add to the stack for the element. So that's the item that I can actually visualize. So with that, maybe hash map may not be actually be part of like the consideration. Rather, it's just set a if conditional statement that's saying that the time is more or less. I mean, so for this very specific case is that if your time is less, that means your vehicle is running faster, therefore we sort of like, so it is fast, therefore we pop the value. But if your time is like more, that means it's slow, therefore you can add the element into the stack, basically adding the vehicle back to the stack. Yeah, I think that's all for this one. Yep, everything comes to an end.